Hello everyone, and welcome to the video that I have for section 8.5 in our textbook on partial fractions and the process known as partial fraction decomposition. I've abbreviated it throughout this video as PFD. So the objectives for this is, number one, understand the concept of partial fraction decomposition. Number two, use partial fraction decomposition with linear factors to integrate rational functions. And number three, use partial fraction decomposition with quadratic factors to integrate rational functions. The idea behind this, we are going to be working with rational functions in this. So rational functions, if you recall, are in the form, it's going to be in the form where you have a polynomial, n of x, over another polynomial, d of x, where we have our numerator, n of x is the numerator and d of x is the denominator. Okay, and so when we're working with these things, there is some things that have to happen with these, and that's what we'll be taking a look at next. So the main idea here when we're working with partial fraction decomposition is we're going to go and break a rational function into a sum or difference of other rational functions that we're then able to integrate. Keep in mind, so in the past, when you've had a rational function, often you let you do a u substitution, you let u be the denominator, and the numerator happened to be a constant multiple of the derivative of that denominator. But that's not always going to be the case. Okay, so you do have some requirements when trying to do partial fraction decomposition. Number one, the rational function must be proper. In other words, the degree of the numerator has to be less than the degree of the denominator. If it's not proper, then we're going to go and do long division. Or if it's able, we could use synthetic, but generally it's going to be long division. And we're going to rewrite write it as a polynomial plus then the rational function. The polynomial portion we're able to integrate with the basic power rule. The rational function is what's left is going to be what we're going to end up doing the partial fractions with. But if it's already proper, we don't have to worry about this. Number two, you have to be, in order to use partial fraction decomposition, you must be able to factor the denominator into linear factors or irreducible quadratic factors. If you are not able to go through and factor it down to linear factors or irreducible quadratics, then partial fraction decomposition is not an option. And then we have to look at other things at that point, which might even be just numerical methods at that point. But assuming that both of these are true, we're able to do partial fraction decomposition to rewrite that particular rational expression. Now, when we go through and factor it, we're going to, the idea is we're going to have linear factors and we could have irreducible quadratic factors. Well, the first thing we have on this is we're looking at if we have linear factors. So what happens then is that we're going to go through and for each factor, linear factor, in the form of px plus q to the m power, when I do my partial fraction decomposition, it's going to include a sum of these m fractions. Now, so you have a1 over px plus q to the first, plus a2 over px plus q to the second, and so forth all the way down. The idea behind this, we have to go through and include, when we identify a partial fraction decomposition, we have to start out by including every possible denominator that could work that we could have to use to go through and get to a particular sum or difference for these fractions. Okay, some of these constants could end up being 0. It just depends. So, for example, when we look at this problem I have here, 2x over x plus 1 to the third, if I was trying to do a partial fraction decomposition on that, I would look at that as a over x plus 1 plus b over x plus 1 squared plus c over x plus 1 to the third. Okay, I know my part that I would have this, and then I would go through the process that we're going to be seeing later on to go through and identify what these values, the values for the constants A, B, and C. Notice up up here in this portion, we're using some subscripts. We just use A, B, and C here just to make it easier. Okay. Now let's go take a look at what happens when we have the irreducible quadratics. So again, it's very similar. If we do have irreducible quadratics, then for each factor of the form ax squared plus bx plus c to the n power, we're going to have this sum of n fractions. And again, notice the subscript. So on this particular problem here, if I had that example of 3x squared plus 4 over x squared plus 1 to the third, that is an irreducible quadratic. I could go through and I would say that's going to be ax plus b over x squared plus 1 plus cx plus d over x squared plus 1 squared, and then plus ex plus f over x squared plus 1 to the third. And again, we would go through a process to identify all 6 of these constants, which would then allow me to go and do the integration I need to do for that particular problem. Okay. Take a second, pause this here. If you have to go back to the linear factors, make sure you're comfortable with this process. And once you are, let's move on. All right, let's take a look at this first example. In this case, I want to find the integral of x plus 2 over x squared plus 6x. Okay. And so what I do with this one is right away, the first thing I notice is that denominator factors as x times x plus 6. And so what I have then is that I have x plus 2 over x times x plus 6, and my partial fraction decomposition will be a over x plus b over x plus 6. And now we need to identify the values of a and b. So to do that, what we're going to do is I am going to go and multiply through by my denominator. I'm going to eliminate the fraction. So I'm going to multiply both sides by x times x plus 6. And when I do that, I will get x plus 2 equals a times x plus 6 plus b times x. And now what I'm going to do is I'm going to plug in values for x into this expression. So in the first case, I'm going to go through, I'll let x equal -6. So I'm going to plug -6 in for x. So when I do that, I'll plug it into the left-hand side, and I get -6 plus 2, so that's going to give me -4 equals, well, when I plug in x -6 into this portion, that's the -6 plus 6 is 0. So that's going to result in being a times 0 plus b times -6. And so when I solve that for b, I know b then comes out equal to 2/3. 4/6 or reduces to 2/3. Now, I then go through on this. I'll choose another value for x. In this case, I'm, based on this, I need to solve for a, so I'm going to multiply through by, I'm going to let x equal 0. So if x equals 0, I will get 2 equals 6a, and then, so from there I can say, therefore, a is equal to 1/3. So with this now, with a equal to 1/3, b equal to 2/3, I know that x plus 2 over x times x plus 6 is equal to 1/3 times 1 over x plus 2/3 times 1 over x plus 6. And now when I integrate that, when I take the integral on that, the integral is going to then equal, on this case, it will come out to be 1/3 times the natural log of the absolute value of x plus 2/3 times the natural log of the absolute value of x plus 6 plus c. Now at this point you can go through, use the log properties to simplify the expression to combine into one, or you could leave it like this. In this case, if you did use the log properties, the result would be that this was equal to 1/3 times the natural log of the absolute value of x times x plus 6 to the second power plus c. And that 1/3, you could put that as an exponent as well if you wanted to. Take a minute, pause the video, make sure you're comfortable with all the calculations I did here, and that you're comfortable with how the result will give you this particular antiderivative. Once you are, let's move on to example 2. So in example 2, what we're looking at is a situation where we have a repeated linear factor in the denominator. And so in this case, we have the integral of 5x minus 2 over x minus 2, that quantity squared. And so using the partial fraction decomposition, I know that's going to be a over x minus 2 plus b over x minus 2 squared. Now the process at this point is going to be the same. We're going to go through on this, and we're going to go and multiply through by our common denominator to reduce it, to get rid of the fractions. So in this case, what I'll end up with is that 5x minus 2 equals a times x minus 2 plus b. The b will be just by itself because it's constant. So again, when I'm working on these ones, I just go and identify values for x. I'll plug them in a way that I can go and solve for one of the constants. In this case, let's start out. I'll let x equal 2. So on this problem, if I go through and let x equal 2, I'm going to get, I'll get 10 minus 2, so I'll get 8 equals a times 0 plus b. So therefore, b is equal to 8. Now, the next thing I'll do is I want to go through and I need to solve for a. So to solve for a, I really have a lot of different options. I can pick whatever value I want for x, except for obviously 2. So in this case, I'm going to go through and make my life a little bit easier. I have to use a value of 8 for b, and I can just pick any number I want. So let's say I let x equal 0. And if I do that, I will get negative 2 equals negative 2a plus b, but we know b is 8, so plus 8. And now it's a matter of just solving it for a. And then therefore, when I subtract 8 divided by negative 2, I get a is equal to 5. So now I can say that 5x minus 2 over x minus 2, that quantity squared, is equal to 5 over x minus 2 plus 8 over x minus 2 squared. And so when I integrate this one now, I can just go through the antiderivative of 5 over x minus 2. When I integrate it, that antiderivative is going to be the natural log of 5 times the natural log of x minus 2. And now I integrate the 8 over x minus 2. Well, keep in mind, that's 8 times x minus 2 to the negative 2 power. And so I can just use the power rule on this one. And so that's going to be minus 8 times x minus 2 to the negative 1 plus c. Or what I get on this one for my final answer is that the integral of 5x minus 2 over x minus 2 squared dx is going to be 5 times the natural log of the absolute value of x minus 2 minus 8 over x minus 2 plus c. That would be my final answer. Again, take a minute, make sure you're comfortable with the calculations, the procedure I went through. And once you are, we'll move on to the next example involving an irreducible quadratic. Now this particular example, I have gone through and written everything out already, so you can kind of see that whole process. It's because it's a little bit more complicated. What happens here is I have x squared over x to the fourth minus 2x squared minus 8. And the first thing I did is I realized, well, that will factor. That is a factor of x squared minus 4 times x plus 2. And the x squared minus 4, that's a difference of two squares, so that will factor as x plus 2 times x minus 2 times x squared plus 2. And so when I write this out as a partial fraction decomposition, I get a over x plus 2 plus b over x minus 2 plus cx plus d over x squared plus 2. Now, the order of these denominators doesn't matter. That is up to you. So the key part when you're working on these things, especially if you're working with somebody else and talking about some of these things, is making sure that they have the same letters over those same denominators. Otherwise, if you ask what a is, if their a was over x squared plus 2, that's going to be a different problem. Okay, so in this case, we do the exact same thing as before. I'm going to multiply through by my common denominator, by my denominator to get rid of the fractions. And so when I do that, I get x squared equals a times x minus 2 times x squared plus 2 plus b times x plus 2 times x squared plus 2 plus cx plus d times x plus 2 times x minus 2. Now, these ones become a little bit trickier to work with, okay? Now, I tend to go through on this and use what I know, and I will go through on a problem like this one. I'll start out by picking values of x again that will give me something that I can solve for. I can do this. I could work with this in a couple of different ways. In this case, I'm picking, because I have the linear factors, I'm going to go through, pick values of x that will make those 0, so I can then solve for a particular value. But what if I didn't have any linear factors? Well, then what I would have to do is pick values for x and generate a system of equations that I could then solve that system. Okay, but in this case here, I have x minus 2. I let x equal negative 2. When I do that, that's going to be a times that, well, the x squared will be 4, and then a times that will be a negative 4, and this will end up being a positive 6, so I'll get negative 24a, and when I plug negative 2 in for x, this term is going to be 0, so this is 0, and same thing over here. So I get 4 equals negative 24a, and therefore a is negative 1/6. When I let x equals 2, I go through the same process. I get b is equal to positive 1/6. Now I have to go through at this point and identify c and d. In this case, what I can do, I know I can go through and plug in 0 for x, and that's going to eliminate the c. And so when I do that, I put 0 in for x, and keeping the negative 1/6 and putting negative 1/6 and 1/6 in for a. When I plug in 0, I will get when I plug in 0 in here, I'll get negative 1/6 times a negative 4, so I get positive 4/6. And then I get 1/6 times a positive 4, so I get another 4/6. And then plug in 0 here, the c drops off. I get 2 times negative 2 times d, so I get negative 4d. And when I solve that then for d, I get d equals a positive 2/6. I could go and reduce d to 1/3, but when I look at the values of a and b, I see that everything's a denominator of 6, so I'm just going to keep it as a 2/6 right now, just until I finish rewrite the problem. Maybe I'll reduce it then, or maybe it'll allow me to pull out a factor of 1/6. The last thing I do have to do is still find a value for c. Again, I can pick, at this point I can pick whatever value I want. I decided to let x equal 1. And so when I plugged 1 in for x, and I put negative 1/6 in for a, 1/6 in for b, and 2/6 in for d, I was able to come through and get that 1 equals 3/6 plus 9/6 plus c plus 2/6 times a negative 3. And then when I go through distribute the -3, combine these two, and reduce, I get 1 equals 2 minus 3c minus 1. And so going through on this one, do the calculation solving for c, I get c equals 0. So in this case, we know a is -1/6, b is 1/6, and c is 0, and d is 2/6. So what that means then is we have this, that the integral of x squared over x squared minus 2x minus 8 dx comes out to be equal to the integral of -1/6 over x plus 2 plus 1/6 over x minus 2 plus 2/6 all over x squared plus 2 dx. Now what I did here, as I mentioned before, is hey, I can go through and make my life a little bit easier by pulling a factor of 1/6 out. So this is now 1/6 times the integral of -1 over x plus 2 plus 1 over x minus 2 plus 2 over x plus 2, and I'm integrating with respect to x. And looking at that, the antiderivative of -1 over x plus 2 is the opposite of the natural log of the absolute value of x plus 2, plus the natural log of x minus 2, and the antiderivative, I did forget the squared on that one, so let's put that in there. The antiderivative of 2 over x squared plus 2 dx is going to be the 2 over the square root of 2 arctan of x over square root of 2 plus c. This right here is one of the integration, basic integration formulas that's listed in A1. You can use the log properties to simplify this and also distribute the 1/6. If I do that, I could think of that as the 1/6 times the natural log of x minus 2 over x plus 2 plus the square root of 2 over 6 times the inverse tangent of x over the square root of 2 plus c. With that, this does conclude the video. I will show you a different method for going through and solving for A, B, and C in a problem in class. We'll take a look at that. Slightly different. It can help you in terms of this situation we were talking about where you didn't have any linear factors. So with that, I hope that you are having a good day, and I will see you in our next class.